In the last video, we saw that we could represent just a fractional component of a number in binary. And in this video, I want to show you how we can extend that to discuss the actual idea of floating points. So things with like a decimal and a fractional component. So like 1.25, 0.25, these types of numbers we want to be able to represent. And to be able to represent those, we need to first discuss the idea of scientific notation, since we'll be borrowing from that for our different floating point representations. So let's start off by talking a little bit about that just to refresh the idea. The idea of scientific notation is that if you were to take a decimal value, you could represent it instead as a decimal multiplied by a power of 10, right? So for instance, 25 could be represented as 2.5 times 10. It could also be represented as 0.25 times 10 squared. And we could keep going and moving the decimal to get more and more representations of this number 25. Now, decimal numbers, we use this to represent values that aren't, cleanly represented as decimals. Like you have a really, really big number, really, really small number. Scientific notation works great for that. In binary, we use this for our general representation of floating point numbers, any number that has both a decimal and fractional component. So something before the decimal, something after the decimal. And the reason for that is because it's very easy to represent this in compartmentalized pieces, essentially that we can represent an exponent and then one single string of numbers that when multiplied by that exponent give us the value that we're trying to represent, right? So that makes it a really easy way to represent those values. So how do we translate this to binary first off? Well, if I had a number like 25, right, like 11001, it would be equivalent to something like this, times 2 to the power of 1. So if you multiply by 2, it shifts the decimal over, similarly to multiplying by powers of 10, right? So similarly, this is equal to, something like this, which is equal to, say, something like this, and we could continue going on and shifting the decimal value. So this is the kind of representation that we're going to use for our floating point numbers. We'll see that as we continue to develop this idea. And to develop this idea, we're going to start by representing something really simple, which is the number 25. So this will be a really easy one for us to represent. We need 3 pieces of information to represent this number as a floating point. I need to be able to represent the sign of the number. And to do this, I really just need 1 bit. So it's either positive, which is a 0, or it's negative, which is a 1, right? The other thing that I'll need is an exponent. So the exponent is going to be this value right here. So this exponent that we're going to be using. And I'm going to give this 5 bits of space, just as a very simple example. We'll see that IEEE uses different values, but once you understand the general ideas, expanding or contracting these is simple, right? So we have 5 bits as our exponent for this example. And then we have what we would typically refer to as either the significand, or you might hear someone say mantissa. So one of those two, usually people will say for this. I'm going to give this 8 bits. And what this is going to represent is it's going to represent this value here. So the mantissa, or significand, represents the value that will be multiplied by the exponent in order to get the number that we're representing. So the question is, for 25, how do we represent it this way? Well, first off, the easy part is the sign bit, right? The sign is 0 because it's positive, right? Now, what about the exponent? Before we talk about the exponent, we might as well talk about the significand, or the mantissa, right? This probably makes most sense to work from there. So what does the mantissa or significand look like for this? Well, this is the representation of 25. And when we talk about floating point numbers, what we do is we assume that the decimal is at the leftmost bit in this number. So because there are 8 bits for this number, what I do is I place my number in the leftmost bits, and then I pad with zeros until I get to 8 bits. And the question that we're asking is, so if the significand is this, what I'm asking is, what do I need to multiply this from as a power of 2 to move this decimal to its proper location, which in this case for this number is right here, right? And the answer to that is I have to move it 1 space, 2, 3, 4, 5 spaces, right? So this should be 5, or 1, 0, 1, right? And that would give us a representation of our floating point numbers. We have our sign bit 0. We then have our representation of 5 as an exponent. We then have our significand, right? So that's our whole floating point number. Remember that this has an imaginary decimal on the left-hand side. And we're saying if we take this, we multiply it by 2 to the power of this, which is 5. It moves the decimal all the way over here. and we end up with 25. So hopefully that's pretty clear how that generally is working. From here, I'm going to add a few catches and say, okay, maybe there's some problems here that we need to consider. So let's take a look at some of those problems. So going back to our idea of 25, it was pretty clear for us to see that we could easily define a sign, an exponent, and a general mantissa or significand that gives us this value 25. Now, one question that I have is, what if we wanted to represent a negative exponent of 2? So what if I wanted to do 2 to the negative 1, right? In this case, what we would be doing is moving the decimal over to the left, right? Which could be something that we may want to do. Now, in our current representation, we don't really have a way of doing that, right? There's no sign bit for the exponent. There's a sign bit for the actual number itself, but not the exponent. So how do we actually represent that? Well, the traditional way to do this is we say, right now, our exponent is 5 bits, right? And that would let us represent negative powers from 0 upwards to 31, right? And the idea is that, well, we don't really need to represent all the way up to number, 2 to the power 31, right? In this particular instance, that's probably a little bigger than what we need. So what we do instead is we split this in half, and we say everything from 0 to 14 is going to represent our negative exponents. Everything from 15 onwards to 31 represents either 0 or a positive exponent. And that's the way that we're going to divide up that number set. And we can represent this very easily. Basically, what we could do is we could take this exponent, right, and we could subtract it from 15 every time that we use it. Basically, from that, everything from 0 to 14 would result in a negative number. Everything from 15 onwards, well, 15 would be 0, and everything above 15 would be a positive number, right? So that would give us that representation pretty cleanly. So the question is, how do we convert our old representation? Well, for 25, what I had was I had a sign bit of 0 for a positive number. My exponent before was 5. How do I get 5 into this representation? Well, I just add 15 to it. That would give me the value 20 as a result. If I represent the value 20 in binary, in my 5 bits, right, I have 16 plus 4, right? So that would be my representation there. And then the significance stays the same, right? Nothing changes with that. It's really just the exponent that's changing. So significand all stays the same. It's 11001,000. What's happening here now is, so the decimal is still on that left-hand side, as we saw before. But basically, when I do my exponent, I take it and I subtract it from 15. So this value here is 20. I take 20 and subtract it from 15. That gives me 2 to the power 5, which is my original representation, which moves my decimal to the correct place. So we can see that that works, and that seems to be a pretty good approach. So we're happy with that. Great. Okay, so that gives us a nice solution to that problem. So understanding that, let's just take a look at another example that has both a decimal and a whole number component, because I want you to see that sort of process, and then we'll talk about one final problem that leads us into the IEEE floating point representation. So let's say 1.25, right? How do we represent this as a value that is a floating point, right? First off, easiest part, sign bit. Sign bit is going to be a 0 because this is positive, right? We need an exponent. We need a significand. I very much so recommend getting your significand first. It makes most sense to think about it that way. So the question is, okay, so imagine that we have a decimal right here, right? What value would represent 1.25 in this case? Well, if we really think about this, the 1 portion could be represented as just a 1, right? And then if we were to move the decimal right after the 1, we would have 0, 1 for the decimal portion, because 0.25 is represented as just like 1 over 2 to the power of negative 2, right? So 0, 1 would fit that perfectly. So that's really great. That's exactly what we would be looking for. And then we just simply pad this out to our 8 bits of space. Great. So the question is, where do we move the decimal in terms of the exponent? Well, it just needs to move over 1 space. Remember, we want to convert it into that sort of base 15 system that we're working with. So we have this 1 plus 15, which would be equal to 16. So in our representation, it would be, we have 1, 2, 4, 8, 16, right? So that would generally work for us. There we go. So then our binary number representation for this is 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0, remember that there's a decimal over here, right? So if we multiply this by 2 to the power of 16 minus 15, which would be 2 to the power of 1, it moves over one space, and that gives us our decimal number 1.01, which is 1.25. Awesome. That's exactly what we were looking for. So you can see that, as you start to practice this more and more, it will become more and more intuitive. I learned this in school, and I had to practice this, a bunch of times here, even knowing the basic ideas of it, just to get it fresh into my head and just to remember how that's generally working. So, don't feel discouraged if it takes a few practice attempts to really get this into your head. That's no problem. This is a simpler example, so hopefully it makes it a bit easier to sort of get those ideas solid in your head, and then we can take a look at how we can apply this actually to IEEE, right? And just to give you some motivation towards IEEE, because it looks like our system is working pretty well, but there's something that's significantly wrong with it. Oh, sorry, let me just get this back up here. There we go. And the thing that's significantly wrong with it is the following. So we can represent 25 as the following, right? We could have 0, and then 1, 0, 1, 0, 0, and then 1, 1, 0, 0, 1, 0, 0, 0, right? So this was our representation of 25. But it turns out that I have an equivalent representation. Imagine I were to add 1 to the exponent. All I would have to do is just shift all of this number over to the right one, and it would be equivalent. So you'd have 0, 1, 1, 0, 0, 1, 0, 0. Why is this equivalent? Well, if you imagine the decimal, right, if we move it over 5 spaces, it ends up here, which is 25, right? If I move it over 6 spaces from here, I still end up with 25. This leading 0 doesn't impact the magnitude at all, so that's still 25. What that means is that we have 2 ways to represent the value 25. It turns out actually that there's more, right? So I could shift over 1 more, I could shift over 1 more. There's actually technically probably at least 4 ways to represent the value 25. This is a big problem, right? Because now there's a whole bunch of different representations of the same number. We don't really want that, especially when it comes to 0, which is going to have a bunch of different representations in this system. So the question is, how do we fix that? And the answer is normalization. Normalization is going to be the main approach that we're going to see for IEEE. It's the main thing that changes between this approach that I've shown you and IEEE, aside from the bit sizes of everything. But this is really the main thing that is going to change for that system. So the next video, I'm going to show you how normalization works, and then we'll lead that naturally into IEEE, and then we'll move over to the C code again, and I'll just show you what it actually looks like when we disassemble the code and actually just demonstrate that we are actually using the IEEE floating point system in our binaries and show you how you can generally read that. So thanks so much for watching this video, and I'll see you in the next one.